Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we will see about kinetics. First we will start with scope of kinetics. In the early classes of this course we talked about it. Then we will see about mechanism of solid state processes, especially the diffusion and the common notion of diffusion and Fick's first law, where we will cover concepts like activation Gibbs energy for diffusion and vibration and jump frequency. Then we will go to the most important idea of this class, that is diffusivity and the terms inside that. Scope of kinetics for a natural process or a reaction or a transformation or a change in general. Scope of thermodynamics is known to us. That is, we are going to conclude processes are thermodynamically not possible or possible. Okay, the feasibility of the process is given by thermodynamics. When we say some processes are naturally possible, then comes scope of kinetics. Kinetics can stop a process from happening even when thermodynamics permits it. See, kinetically not possible, and then there are kinetically possible processes. The focus is not much on whether a process is possible or not, because the moment there is a thermodynamic green signal, then kinetically the process will happen at different rates. That is more important. Okay, the rate at which processes occur, that is more important when it comes to kinetics. And when we talk about rate, what is important is mechanism of the process. Atomistic level, what is the picture of any process, and that is the mechanism of a process, and anything that intervenes with that mechanism is going to intervene with the rate of the process. Okay, so that is where we talk about mechanism. And in solid state, if you see, most of the processes, they happen by this mechanism of diffusion, solid state diffusion, and we will be focusing on that particular aspect in this class. So this is the scope of kinetics. When thermodynamically a natural process is permitted, then kinetics tells you what is the rate of the process. Okay. Okay. About diffusion, if you take let's say a solid alloy, copper with 20% nickel, and another alloy, copper with 10% nickel, and join them at 800 degrees, keep them at that temperature for a long time, then it will become copper 15% uniform everywhere after certain time. Basically the equilibration time I am talking about. Okay. So we know this is possible in copper nickel system. This system you have seen as an example for an isomorphous system. That's why it is possible. But if we put it in a concentration profile kind of thing, like this, concentration of nickel versus distance, initially this is how the nickel content was. Initially in one side of the material it is 20%, in the other side it is 10%. This is the initial state, and with respect to time it actually changes, and eventually it becomes like this, and this is the final state where everywhere nickel content is same. This is known to us. This is a process of homogenization where composition differences vanish, and the mechanism by which this process happens is diffusion. Atoms diffuse, copper and nickel interdiffuse in both the regions, and everywhere it becomes same, right? So the process kinetics here is understood by the changes in concentration profile with time. You see, we started with this step profile, initial condition, and then it slowly started becoming like this. After a certain time it is like this, then eventually it reaches this state. So what are we doing here is essentially tracking the concentration profile, and based on that we can say how is the process is progressing. So ultimately in many of the processes we should try to get the concentration profile, and that will give us an indication about the kinetics of the process. So when we talk about diffusion, the common notion of diffusion is this, that is diffusion happens over a concentration gradient. We think that concentration gradient causes diffusion. You think like this, there is a material here, and let's say there are some interstitial atoms within a bigger atom cell. Let's say iron is the bigger atom and carbon are these interstitial atoms. If at all there is a configuration like this, so one side we have more carbon, one side we have less carbon. If this is so, there is a definite concentration gradient. If there is a concentration gradient, we generally tend to think that with respect to time, the atoms will diffuse and everywhere it will become uniform, right? So that is the common notion. But why it happens? Do the atoms think and decide to move from high concentration region to low concentration region? Or the atoms here know that there is a less concentration this side so that we can move from here to here? Is there anything like that? Yeah. So let's look at it, unpack it and understand. That's where Fick's laws come. Fick's laws we'll try to understand, and from that we'll also get to this property of diffusivity. At atomistic scale, this is what we are talking about when we say diffusion. Let's say there are these 6 atoms here and there is an interstitial atom here. And now if these atoms move from this location to this location, okay, from here to here, meaning it breaks all the bonds here. Let's say there are 4 atoms here, possibly there is one atom in the front and one atom in the back, in the third dimension I am saying, in front of the screen and below the screen. So that is the 6 atoms to which it is bonded here. It breaks all those bonds and jumps to this point and making all those bonds again. Okay, that's the point of this jumping. Okay, but you can sense that while jumping from here to here, it has to undergo some kind of a pushing of these atoms. Only then it can move here. Okay, this is what diffusion is, and based on this we can understand several things. So this picture is important. Now let's consider this sort of thing that we had, that high concentration of carbon on one side and low concentration on the other side. This we will take and we will decide 2 planes. We'll find 2 planes in that, where concentration is high in one plane, 3 atoms are here, and the other plane has 2 atoms. Okay, so these 2 planes if we consider, one, let's say B atoms are interstitial atoms, so this B, and these hollow atoms are the parent lattice atoms. Okay. So planes 1 and 2 both have unit area. Area, this is just a line drawn here, 2-dimensional case. So this is like a sheet going through this, going perpendicular to the screen. So you can imagine 1 and 2 as 2 planes. Number of atoms, if you consider, N1 is the number of atoms in plane 1, N2 is the number of atoms in plane 2. Because we are not talking about these 3 and 2 here, we are talking about the entire plane. Okay, there may be more atoms in plane 1 and more atoms in plane 2. Okay, but the number of atoms in plane 1 are more than number of atoms in plane 2, that is N1 and N2. Okay, this is fine. Then B atoms randomly jump. So we want to find the answer to this question of whether the atoms are just randomly jumping or are they trying to go there, there is a driving factor for them to go there. So we want to say that it is randomly jumping and see whether any flow can occur, any flux can occur with this random jump. That's what we are going to probe. Okay, so B atoms randomly jump. If they randomly jump, what will happen? That's the question we are asking. Okay. To answer this, we need to find the flux of B atoms in the forward x direction from plane 1 and backward x direction from plane 2, and to check for any net flux. That is what we are going to do. So from this plane, that we'll calculate the flux for atoms to move forward, and from this plane we'll calculate the flux for atoms to move backwards. Basically what we are probing is whether from high concentration to low concentration flux will happen, or from low concentration to high concentration flux will happen. Okay, if there is a net flux which is in a particular x direction, either forward or backward, then we can conclude that atoms are still randomly jumping, nevertheless there is a flux appearing. Okay. So flux is number of atoms moving per unit area per unit time. We have to see whether there is a flux happening in that high concentration to low concentration region. Right. So to understand that, 2 more important concepts we need to know. Let's bring that picture of an atom trying to jump. So here the atom is, and if the atom is nicely sitting here, this is basically bonded like this because of lowest energy configuration. The Gibbs energy wise, this bonding makes it lowest. So that's why it is there. So therefore, if we plot Gibbs energy versus the distance where the atom is sitting, based on that, if we, this configuration will have lowest Gibbs energy, that's why it is stable, right? Now imagine this atom has jumped here, okay, the right extreme figure, this one, where the atom is in this place, and this is also a stable location. then the Gibbs energy corresponding to this configuration also would be this. So the Gibbs energy before and after are same, but in between what happens is this kind of configuration where this atom is trying to move and it is here stretching the bond between these two atoms, and it is also in an upward position. So this particular bonding is not favored, therefore the Gibbs energy of that is higher. This is the reason why it is not favored. So Gibbs energy is higher. Okay, so basically stretching the bonds, you can imagine the potential energy curve. If the bonds are stretched, the energy goes up, right? So that is what is happening here. The Gibbs energy is higher here. This total height of this hill, that is delta Gm. Delta Gm is called as Gibbs energy of migration or activation Gibbs energy of diffusion. Okay, so this is basically like a barrier for the atoms to jump. So next important idea is this vibration frequency and jump frequency. We'll understand with this example. Take carbon atoms in steels. Okay. They vibrate 10 power 13 times a second at 1000 degrees Celsius. Imagine one atom is vibrating 10 power 13 times approximately. Okay. Will every atomic vibration result in a jump? Okay. The answer is no actually, because only vibrations with energy beyond delta Gm will jump. Atoms are vibrating and some vibrations will be particularly violent and they will be having energy higher than delta Gm. Only those vibrations will result in a successful jump. Okay, this nu is vibrational frequency like this 10 power 13, and among that only a part will be successful jumps. So that successful jump frequency is this gamma b, capital gamma b. Okay, so now with these two ideas, let's go back to this planes 1 and 2 which have unit area and number of atoms there are N1 and N2. Now flux of B atoms in the forward direction, x direction from plane 1 and backward x direction from plane 2. We are going to figure it out. So this is in the forward direction. You can understand how it comes. Imagine an atom has how many options to jump. So forward, backward, top, bottom, front and back. So it can come to forward, this side and backward. Okay, so there are 6 positions for it to jump to. Among these 6 positions, only one is in this forward direction, right? So 1/6 of the total options are in the forward direction. So 1/6 is the probability to jump forward. So let's take that probability 1/6, multiply that with jump frequency. Okay, so in the jump frequency, only 1/6 actually is the frequency to jump in the forward direction. Okay, so that is the frequency for jumping forward for one atom. For N1 atoms, this is the jump. So this is basically the number of jumps happening per unit area per unit time, because anyway frequency is expressed per unit time and we are talking about planes of unit area, right? Therefore, we are talking about per unit time per unit area how many atoms are successfully jumping. That is forward direction flux of B. In the reverse direction, we are talking about from plane to reverse direction, right? So we have to put N2, and since it is reverse direction, we are putting a negative symbol here. So N2 is going to give us number of atoms in plane 2 and multiply that with the jump frequency of 1/6 of jump frequency, we will find out the backward flux, right? Now if you join both of them, you get the net flux in the x direction, that is 1/6 gamma b N1 minus N2. As long as there is a N1 minus N2, this is a positive quantity, isn't it? So the net flux is in the forward direction because N1 is bigger than N2. Okay. Okay, for me, Fick's laws end here. We have to bring it to a final shape and talk about diffusivity and all. But there is a net flux when the atoms are randomly jumping. The very reason for that is the number of atoms on one side are more compared to the other side. So if they are randomly jumping, eventually there will be a net flux from the high concentration to low concentration. Okay, so net flux is in the x direction is happening, and if we convert this N1 minus N2 in terms of concentration, concentration is formally defined like this: number of atoms in unit volume. Okay, if we bring that into picture and also take the fact that this distance from here to here is alpha, that is the thickness of the planes, and if you take the area and thickness, you will get some kind of a volume between the two atoms. So that is the volume where this N1 number of atoms are there. Okay, if you bring that into picture, you can convert this N1 minus N2 to alpha square dou Cb by dou x and negative N2 minus N1, you can reverse it and put a negative symbol here. And if you want the detailed derivation, you can go to this book. It's only a couple of steps I am orally explaining. So once you do that, you have this dou Cb by dou x coming. This is concentration gradient. Okay, concentration difference over a distance. Okay, that is going to look like this. You see, concentration is plotted against distance, and high concentration to low concentration is how the initial configuration is. So in this point to this point, these are the two different concentrations we are talking about. N1 and N2 are the number of atoms there. Okay. So the height here, the y-axis length here is going to be alpha multiplied by the slope. Okay. The x-axis distance multiplied by the slope will give you the y-axis distance. Now we have this dou C by dou x coming. Okay. So this height here is alpha multiplied by the slope. The slope is dou C by dou x, and alpha multiplied by the slope will give you this height here. So if you bring that into picture, you will have this expression, and here you can convert all these things into dB, diffusivity, and concentration gradient can come here. So flux is equal to concentration gradient multiplied by the diffusivity. That is Fick's first law, and the diffusivity is this. Essentially, we are talking about these successful jump frequencies. Okay, how easy is the jumping? Based on that, the diffusivity is going to be influenced. Of course, there are more to it. This alpha square is the distance, diffusion distance. That's also going to matter, and the probability of jumping in one direction, that also matters. Right. So this is called as diffusivity or diffusion coefficient. We'll be using these words throughout these kinetics classes. So let's spend a minute on diffusivity and understand it a little more. Let's say this is a material M, and the element A is there in this material. The concentration of that element A is 1 here and 2 here. Okay. So if concentration gradient has this kind of a shape, in this material, how the diffusion will happen? It will happen based on what is the diffusivity of this element A. Right. So if we take the same concentration but in a different material, okay, it's a different alloy, where A element is still there, but the exact concentration gradient is there. High concentration in the left side and low concentration in the right side. Okay, exact value Ca1 and Ca2. Will diffusivities in these two materials be same? Okay, let's say this is an alloy of chromium nickel. This is an alloy of chromium iron. So chromium is diffusing in iron, chromium is diffusing in nickel. Will there be difference? Obviously yes. Here the diffusivity will be through M, here the diffusivity will be through N. Okay, so it is, the question is not only about which element is moving, the question is also about the element is moving in which environment. Okay, here it is M material, here it is N material, so that matters. So when we talk about diffusivity or diffusion coefficient, we have to be careful with this. Unlike most of material properties, this diffusivity is defined for a species in an environment. It is not only about the species. Let's break down and understand diffusivity more. First, we will ask this question of what is this gamma B and understand it further. To understand it, recall this one, thermal equilibrium and Maxwell-Boltzmann distribution. We have seen this. Okay. Maxwell-Boltzmann distribution occurs in any material in thermal equilibrium, meaning the atoms are continuously exchanging their energies, and there will always be a distribution of energies, distribution of velocities in which atoms move. Okay, or the vibration, if you think about solids, you can think about different vibrational modes that an atom can achieve. There will be a distribution for that particular vibrational frequencies. There are always some number of atoms which have really high energy, some number of atoms with low energy, and so on. There will always be a distribution, and this is the distribution. That temperature T1, it is like this. If you go to a higher temperature, the distribution shifts towards the right. As the temperature increases, the distribution shifts towards higher average velocity or a higher average energy. Okay. So with this idea, we can get number of atoms or fraction of atoms with minimum energy to jump. Okay. So energy distribution occurs a fraction of particles will have energy delta Gm or higher. Okay, not all atoms, only a fraction of atoms will have delta Gm or higher energy with which they can vibrate. Okay, the higher the temperature, the more will be this fraction, obviously. So on average, the fraction of atoms, meaning specific atoms divided by total atoms, okay, with an energy of delta Gm or more. Okay, how many atoms will have the specific atoms mean how many atoms will have energy delta Gm or more divided by total atoms. This fraction we can calculate using this expression. Okay, this is a very powerful expression. You might have seen exponential minus energy by RT in many places, Arrhenius form, and this means that in the total how many are having this energy or more. That's the meaning. Okay, in the total, that is in the denominator, how many, that is in the numerator, have energy delta Gm or more. Okay, that can come from this expression. Exponential of a negative value, that delta Gm is some sort of energy divided by RT. If you multiply gas constant with temperature, you will get an energy unit. So two energies, if you get the ratio of that, this ratio or negative of it, if you take an exponential for that negative number, you are going to get a fraction. Okay, and that's going to be the number of atoms with the energy this value or more. Okay, so with this term we can understand diffusivity better. The mean frequency of vibration is nu, that is just the vibrational frequency, and every atom is surrounded by Z sites to jump, right? Then how many atoms are made to jump? Okay. In the new vibrational frequencies happen which are like atoms to jump to these Z sites. Okay, that is the total number of atoms made if you multiply these two things. And how many are successful in that depends on whether they have enough energy delta Gm or more while they are vibrating. Okay, so gamma B is equal to Z nu exponential minus delta Gm by RT. Z nu is the total atoms for vibration. Okay, these are total atoms. New vibrational frequency to Z sites, so that is the total atoms, and in that a fraction will be the successful jump. Okay, so multiply that with this. Okay, so since we have this delta Gm, Gibbs energy of migration, we can split it into delta H and T delta S part. Okay, so we can write exponential minus delta Hm by RT, then minus T delta S will become plus T delta S because there is already a negative symbol. My plus T delta S divided by RT, and these two T's will get cancelled and delta Sm by R will remain here. That term we can take it to the forward here, Z nu exponential delta Sm by R. These things we can group together, and exponential minus delta Hm by RT we can keep separately. Now if we take the dB, which is 1/6 of gamma B alpha square, substitute this gamma B expression there, we are going to get this full expression. Okay. Here we can group these parts 1/6 alpha square Z nu exponential delta Sm by R, all these things to D naught. Then exponential minus Q by RT. Exponential minus Q by RT is now separate. This Q is here used instead of delta Hm, that is to call it as activation energy, a new symbol is given Q. Okay. So this D naught and Q are what people understand who work on diffusivity, because D naught and Q are reported experimentally. For a temperature range, Q is not going to change. Say Q is basically the energy required to break bond, right? And that is going to be one value for a temperature range. And for some other temperature range, it's going to differ. So this value is kept separately. Okay. So I will show you how it is figured out also shortly. This is like a summary where diffusivity is expressed like this: D naught exponential minus Q by RT. This D naught is called as pre-exponential factor and Q is activation energy. Okay. So I am putting couple of sentences because we have spent so much time understanding thermodynamics. This should not be difficult for you to understand. That's the reason why I am putting this here. The enthalpy of diffusion, this Q part, activation energy, is the difference between the migrating atom's potential energy in the activated and stable state. Okay. So migrating atom's potential energy in the activated state is when it actually stretches the bonds and tries to sit in that awkward position, right? That is the activated state. Stable state is the state before that or after that, where it reaches the minimum energy state. And that difference between activated and stable state is called as enthalpy of diffusion. The entropy of diffusion is a measure of the ratio between the migrating atom's number of vibration energy states, W, in the activated and stable states. So when it is in that activated states, it will be in that awkward position and the vibrations will be different. Okay, the number of vibrational modes it can access, those things will be different. So you can calculate a W there for the vibrational energy states and W in the stable state. Okay, based on this, you can calculate an entropy change. Right? That is basically the entropy of migration. Right? So experimentally, when we do the diffusivity measurements, this is how it is reported. This equation is taken and the logarithm is applied to this log dB is equal to log d naught plus this minus q by RT will come here because it is not a natural log. We are putting 2.3 extra here. Okay. And then 1 by t separately is written. Basically to show you that this is having this y is equal to mx plus c form. Y is log dB. You can see log d is plotted here is equal to c. This is log d naught is c here, and mx, m is minus q by 2.3 r and x is 1 by t. You can see in x axis 1 by t is plotted. Okay. So the slope is going to be minus q by 2.3 r. So if you want to figure out the activation energy for diffusion, then plot this log d versus 1 by t. The slope is going to give you the activation energy by r. So you can calculate that in this way. So d naught and q are reported for different temperature ranges, for different materials, different elements, let's say different species in different environments. So that diffusivity data is important to understand how atoms move according to the Fick's first law, how we can calculate flux and understand the kinetics of processes. And of course, Fick's first law is quite limited. We will see about Fick's second law in the next class and see how it applies to more real life scenarios. And that's where the diffusivity becomes really powerful. We'll see about that in the next class. Thank you. I hope the lecture is useful. See you in the next class.